called up with a postdoc at University of Virginia. And then he went to another second postdoc at the CITA, Harvard. And then he joined the faculty at the University of Illinois, where he's been ever since. He's an expert on numerical astrophysics, MHD, hydro, and he's done a lot of work on solving MHD in the vicinity of black holes, and I think he's going to tell us about some of that today.
Okay, thanks, Sinead. I should say this is the first time I've given a talk on any of this stuff, so it may be a little rough the first time, but I'm interested in your questions. And I also want to mention that the Department of Physics now has a position for postdocs, so I'd be happy to talk to the postdocs along here. Okay, so here's an outline of the talk. First off, I'm going to talk about the numerical work we've done to build up a set of codes to model accretion flows near black holes and to model the emergent radiation field. And then I'll go on and talk about 3 different applications that I've done in collaboration with students and postdocs. So the first issue I'm going to talk about is convergence of the fluid dynamical models. And this is work that I've done mainly with a student, Otaka in Chicago. And this is sort of a natural follow-on to some of the work that people have been doing in local model simulations, accretion collection, looking at convergence of the local context. Then I'm going to talk about pair production in our models. So the idea is that we have a self-consistent model of the radiation field near the black hole. And from that, we can calculate the rate of pair production due to photon-photon collisions. And this stuff was done with a postdoc, Monica Rush. Then finally, I'll talk about QPOs, quasi-periodic oscillations. So we built models that specifically are designed for the galactic center. And in light curves from those models, we found quasi-periodic oscillations. And so I'll tell you a little bit about what we know, and then why you shouldn't completely believe what we've done. Okay, so start with the numerical laboratory. So motivation for this work is to model weakly radiative systems like the galactic center and like M87. So this is the universal icon for the galactic center showing stellar orbits. As most of you know, this is a system that we understand relatively well compared to stellar mass black holes. We know the mass, we know the distance. We actually have constraints on the size of the source in a millimeter from direct VLBI measurements. So this is a very, very slowly accreting source, we think, if the models have anything to do with reality, with a ratio of accretion rate to the Eddington rate around 10 to the minus 8. M87 is probably a more rapidly accreting system. Again, the models don't have anything to do with reality. Probably a ratio of accretion rate to Eddington accretion rate closer to 10 to the minus 5 or 10 to the minus 4. Okay, so that's it for the motivations. Let's move on and talk about the models. So these models have 2 components. One is the relativistic fluid mechanics that models the plasma flowing onto the black hole. And we model this using a relativistic MHD code that I developed in collaboration with students, Jonathan McKinney, and also with a postdoc, Scott Miller. And we integrate the equations of relativistic MHD in axisymmetry or in full 3D. And And the models are fully relativistic. They're integrated in the Kerr metric in Kerr-Schild coordinates. So we can follow the fluid flow down through the event horizon, singularities. And they are either non-radiating or now weakly radiating. So we've run some models in which we allow for synchrotron cooling. And my student Josh Dolans has developed a model which couples, or code that couples the fluid dynamics to the radiation field. And just to show that this is now widely accepted textbook stuff, there's the textbook code. Okay. Actually, it's a pocket. I'm time limited, so I'm not going to cover the equations we're integrating, except to say that we are using a fluid approximation here, which is a very serious approximation. So the mean free path along the field lines for sources like Sag star, where the density is very low, the accretion rate is very low, are something like 10 to the 5 times the event horizon radius. So these are pretty collisionless plasmas that we're modeling using the fluid code. Okay. And as a result, we don't capture potentially interesting effects like anisotropies in the distribution function or conduction. Okay, so here's an image of one of the models. This is a slice through the equatorial plane in a particular coordinate system, and the colors show density in the equatorial plane, logarithmic density actually, around a black hole with a spin of roughly 0.9. And I'll show you a movie of this. Okay, so the simulation, all our models start with a torus of plasma orbiting the black hole. It's a fluid equilibrium, and then we embed a weak magnetic field in it, weak in the sense that the magnetic pressure is small compared to the gas pressure. And there's a MHD instability that drives this system unstable and leads to angular momentum transport. So this instability allows the fluid to change its, or the turbulence driven by this instability allows the fluid to change its angular momentum. And so some of it accretes onto the hole. You can see the densities gradually going down as the simulation progresses. So some of the material accretes onto the black hole. I think it's around 20% in this particular simulation over the course of the entire run. And then some gets lost through the outer boundary at 40 GM over C squared away from the black hole. And this is, up here, this is time in units of the light crossing time through the event horizon. Okay, so the picture is we set up this initial torus, it becomes turbulent and establishes a quasi-steady state, and then we use that quasi-steady state to develop our radiator models. Okay, so the second piece of the numerical laboratory is radiator transfer. And in all these models, we include only synchrotron emission and absorption and Compton scatter. So we have two ways of doing this. One is using a time-dependent Monte Carlo code, and the other is using a time-dependent ray tracing code. So the only kind of novel aspect of this is that the light crossing time is comparable to the dynamic time scale in these systems. So we have to follow the photons through time slices as the system evolves. We don't do radiator transfer on individual time slices. This one does in a non-relativistic So this image over here is an outcome of one of the time-dependent ray tracing calculations in a model meant to mock up Sagittarius A star with an inclination of 85 degrees, and this is a 1.3 millimeter image. So this is meant to model the VLBI observations that people like Shep Goldman and collaborators are carrying out. Okay. So here's the movie of this, and there's a lot of interesting physics in here, actually. But first, let me just explain what you're seeing. So the colors are coded to the logarithm of intensity on the sky at 1.3 millimeters. And this structure, if it were Sagittarius A star, is about 50 microarcseconds across. So let's let it go. The underlying fluid calculation is fully three-dimensional, and it has no cooling in it. Okay, so you'll see that it's brighter on one side here, and that's because the plasma is circulating around the hole, and it's Doppler boosting the emission towards us on the approaching side, on the left-hand side. And it's dimmed over here. And then we see the plasma as it circulates around the hole, so it goes, you can see the fluctuations moving this way, and then they go up over the top. And that's gravitational lensing. So lensing is very important for those photon energies that are produced by the plasma very close to the black hole. So that is a model that's a millimeter wave and higher frequency.
To what extent do you see discrete structures? Hotspots?
You don't really see hotspots. But I'm going to talk about QPOs in a minute. So it's really a very noisy system. And the punchline of the QPO stuff is that lensing acts as a sort of filter to pick out particular frequencies.
You expect to see hotspots. This is the temperature here is just your equation of state is just. What is your equation?
Okay, so equation of state is gamma 13 ice. So that's appropriate when electrons are relativistic, electrons are non-ice, which is what's going on. You might see, but it's not
obvious. You could have localized heating from your connection.
It's, you could, and you do, if you have numerical connection.
You have a single temperature.
No.
You have two temperatures? You have different temperatures between the electrons and the protons?
So in the radiator models, we allow for a temperature ratio between photons and electrons, but we're not solving any electron energy equation, if that's what you're asking. The temperature is not uniformly positioned.
No, I know that. But the if you allow, so you don't allow the electrons to cool they don't get accelerated up.
No, we don't. We have the electrons in the Sagittarius star models are factor 3 cooling. And
But
Is that just built in?
no, we can vary that parameter.
Well, but that's what I mean. It's a parameter.
Yeah.
It's not solved for the model.
No. So a natural thing to try would be to do the kind of thing that Elliot's done and allow the electrons to evolve in a more self-consistent way. But I can tell you that we varied that parameter and found that if we make the electrons very cool, then the VLBI source gets too big. So there's a constraint on the electron temperature, or effective electron temperature. Okay, so those are our two components, the fluid calculation and the radial transfer calculation, which for now is mostly done as a post-processing step. Okay, so convergence, and you might wonder whether we're accurately modeling the fluid dynamics. We've spent a good deal of effort on this and millions of CPU hours. We've done a series of models at different resolutions and looked at various measures of convergence. So there's some obvious things to look at. So the radial profile of shell average dimensionless quantities like the plasma beta, the ratio of gas pressure to magnetic pressure, or the radial profile of dimensionless temperature theta, which is just the temperature needs of the electron rest mass. We've also looked at correlation lengths of various fluid variables. So correlation lengths of the magnetic field, density, and internal energy. And this is useful because we think the correlation length corresponds to sort of the average scale of the turbulence driven by the rotational scale, driven by this MHD stability. And then finally, we've looked at spectra. So are the spectra consistent from one resolution to another? And there's been actually a fair amount of activity in this area lately. So Hawley and collaborators and Beckwith, Chris Beckwith and collaborators look at similar issues in non-relativistic fluid calculations. Okay, so first radial profile convergence. So let me tell you what you're seeing here. So this is the radius in units of GM over C squared. And this is the plasma beta ratio of gas pressure to magnetic pressure. And we looked at different boundary conditions of the pole. So things are consistent from one boundary condition to another, so you can ignore this for now. So the very low resolution simulations tend to produce higher beta, so weaker magnetic field. And then as we turn up the resolution, the magnetic field strength comes down and seems to be close to constant with radius outside the innermost stable circular orbit, which lies about here. So event horizon is here, innermost stable circular orbit is right about 2 and so you can see that plasma beta is changing a little bit as we go to our highest resolution calculation, but not by much. It goes from about 20 out here in the bulk of it is to about 50. So we seem to be at least getting close to a converged state.
Yeah, no explicit resistivity or
We have, yeah, that's correct.
So
So,
it's just rigid velocity.
correct.
Resolution is too long. Get a lot of it.
Yeah, I think that's just fine. So this stuff has been sort of controversial over the last 4 or 5 years because people found non-convergence in some of the local model calculations. So local model calculations are a little box that studies one section of the disk. And I think there's really only one class of calculations in which convergence is not found, and that is zero net field, zero dissipation model, and zero stratification. So if you introduce any one of those factors, the models appear to converge. Well, that's cold comfort because the fact that it depends on that is a little unsettling. Yeah.
This is maybe slightly uncovered. Can you comment on the computational feasibility right now of studying the transport of magnetic flux and the geometric effect flow?
Yeah, Chris Beckwith is going to know a little bit on that. Yeah, it can be done. It's a little more numerically sensitive because there are stronger fields in some of the low density regions of the calculation that just make it more likely to crash. Yeah, but that's an interesting question. Okay, so other parameters, temperature, and this is an important one because it governs the immersion of radiation. Also seems to be pretty well behaved. So the difference between this moderate resolution guy and the 2 times higher resolution guy is only about 10% in temperature. So we seem to be doing pretty well on temperature. Okay, but what about the structure of the turbulence? What about the correlation? Before going into that, I just want to mention some of the local model work that people have done to show what one should expect. So this shows a correlation function computed for one of these local model simulations, and this is essentially radius, and this is an azimuthal coordinate, and these are all in units of disk scale height. And you can see that the sort of natural structures that the turbulence forms are little trailing spirals of magnetic field that are narrow in one direction and elongated in the other direction. And if you take a cross section through this, either along the minor axis or along the vertical axis, you see that the cross section, these things are very, very narrow. A small fraction of the scale, 0.03 scale heights. Along the major axis, they're quite large, 0.2 scale.
Was that a stratified calculation?
These are unstratified calculations, but actually these results are typical of what people are seeing in the stratified calculations, and I'll show you them on the local calculations. So it happens to be similar because of the field that we imposed in this particular unstratified. There's a sound speed. So sound speed over rotation frequency. So it's sort of a scale which compressibility becomes important in the local models. Okay, so here the picture is pretty mixed. So for the density, internal energy, and temperature, we seem to be getting reasonably good convergence. So all these plots show resolution along the bottom axis. This is the radial component of the resolution. And then the azimuthal correlation along the vertical axis. And then on each plot we put in the, this is 2 grid zones, azimuthal correlation like this is 5, this is 10. Okay. So you can see that the density correlation length is about 10 grid cells at the highest resolution. And so that's reasonably well converged. But the problems lie with the magnetic field. So here we're just barely starting to see some increase in the correlation length in units of the grid cell as we increase the resolution. So lowest resolution, highest resolution. And what we expect from the local model correlations functions that I just showed you are correlations lengths of maybe 0.025, so we're down about here. So we think that with another factor of 2 in resolution, we could actually resolve the magnetic field correlation length. But that would require about 16 million hours of CPU. So it's a hard proposal to write. Okay, so having said all this, does it make a difference when we calculate the emergent radiation field? And The answer seems to be that for now, at least for the resolutions that we have access to, the spectra are only weakly sensitive to that non-convergence of the magnetic field correlation line. So this shows a model. We have to put characteristic scales into the model when we run the radial transfer calculation. And here we've put in scales that are appropriate for the galactic center. So a mass of 4 10 to the 6 solar masses and an accretion rate of about 10 to the -8 of Eddington. So this is a pretty typical spectrum. The source produces a synchrotron bump here. And then it produces a couple of Compton scattering orders. So it produces synchrotron photons in the torus, and then they scatter off these 10 to the 9 or 10 to the 10 electrons into the X-ray or into the gamma rays. So you can see that as the resolutions increase, the position and height of these things don't change that much. So we're pretty pleased with this result. But I should tell you that there's a little bit of focus in this, in that we have to normalize the simulation, normalize the density as a function of time, so that the flux is correct at 1 millimeter. So just to back out for a moment, we're doing this so that we can model a quasi-steady accretion flow. And our numerical model has a torus, a plasma, that accretes onto the black hole over time. So the density goes down as the system evolves. And we have to somehow match that onto a time-steady model. So we change our normalization in a smooth way that it's motivated by by classical accretion disk theory. So we use an analytic solution from viscous disk evolution theory, and that takes away most of the variation of time.
Did you try to go to the sizes?
Sorry?
Did you try to do the close, slow close, just to see if there's any difference?
Yeah, we've tried slightly different size tori. We can't make them much smaller because then they're inside the black hole. And we can't make them much bigger because then the evolution time scales get to be really, really long. So we're numerically constrained.
You expect the, oh, sorry.
Right.
You expect the magnetic field structure to depend on the size. 40 GM and this is going to look like this size.
I don't think so. These things evolve so that the ratio of the scale height to the radius is approximately constant with the radius. So, because of the coordinates we're using, that always corresponds to some fixed number of grid cells at different radii. The way I think a larger torus could make a difference is if there's a magnetic interaction between the material of larger radius and smaller radius. That's not clear.
I was wondering that with the resolutions are very close together, and the very high resolutions are quite a bit further away.
Yeah, so basically this is driven, the way you can think about this is that we've normalized away the change in magnetic field strength. And that reflects the change in temperature, which is about 10% between the moderate resolution and highest resolution of these simulations.
Just you may, there's something about the optical depth, right?
Yeah, so
if you're just scattering enough of voltage contacts to make the next one.
so the position of this in frequency is related to the temperature, and the height is related to the optical depth, and then some product, some factors.
Yeah. Now, if you get the right height, right absolute millimeter flux,
Yeah.
then you naturally get the right optical depth to give you the relative height of the next one, or you have to sort of fiddle to get that.
Yeah, so have we built in the answer? I think the answer is I think that if we had a different emissivity producing a low frequency bump, that this could be very different. And so it's really a fortuitous thing related to the structure of the synchrotron emissivity.
Which is confiscated, right? The bump is.
Yeah, the bump is confidence.
Yeah, that's why I didn't say output that. I mean, maybe you're basically looking at energy density. And the photon field and then magnetic field. And then the traction of the photon field is
So the real example is unconditional by the white constant, which is the point of the convection.
Yeah.
The original was
Well, more, with the observation connections, is it actually, I mean, I know there's flaring and quiescent, but the quiescent is actually below that. 10 to the 34 or something.
I don't have the number off the top of my head. This is just a test model
Sure.
that's close to the electric parameters. This thing does move around as the simulation progresses. So it changes in the output that one feels right.
Give an outflow.
Yeah. That's a whole other topic.
Can I just ask what?
Yeah.
Did you vary the geometry?
You know, so that makes a difference for the evolution of the polar regions, but it seems not to strongly affect this. So, same disk, different check. Okay, so.
Well, there are assumptions in your course. You basically assume that you're creating from something like
Yeah, which has a
KV,
fairly-
like KV temperature, interstellar medium, right? Not something more relativist. I mean, if you get black hole coughing off relativistic plasma, then there could be, in fact, quite different things going on in this vicinity than the simplest, generally accepted. I mean, the plasma doesn't have to be anything, something that is cold or relatively cold and primarily brown.
I suppose. I think that in the Galactic Center we know what's a little bit about what's going on. 100,000 geometers is where from the black hole. And there's a region where we have very few probes. In the immediate vicinity of the black hole is producing this synchrotron machine. So I've given you the most pessimistic possible view of the numerical model. And now we're going to use this to investigate a couple of physical effects near the black hole. So the first has to do with air production. So these numerical simulations all have a region over the poles of the hole, which is almost empty. It has a well-organized field, and there's nothing to hold the plasma in those regions. If you put a blob of plasma in there, it either falls down into the hole or gets thrown out to infinity. So there's a question about what populates plasma in that region of the simulation. And in a numerical simulation, it's done with numerical tricks. So we have a floor in the density, and we put in stuff when the density goes below the floor. But physically, that's not what's going on. So one possibility is that there's a contribution to the plasma density through pair production from gamma-gamma collisions. So it's an otherwise empty region. The only thing out there self-consistent model of the radiation field, so we can just go in and calculate the rate at which flares are produced. So we have an empty funnel. What determines the density? Okay, so if the density is low but not so low that there isn't enough plasma to short out the electric field, so in other words, if the density is above, substantially above the Julian density, then these photon-photon collisions are probably going to dominate the production of the paraplasma in the funnel. So again, self-consistent model for the radiation field. Then we can go into just Monte Carlo, the paraproduction rate density. And this is our invariant expression for the paraproduction rate. So we integrate over the photon distribution functions, and then there's a cross-section here. And we do all this in the ordered frame, actually. All the wave numbers for the photons are specified in the ordered frame. And this leads to an invariant paraproduction rate density.
Is there a significant computational burden?
This is done after the fact, so it's actually fairly time sensitive. So some of these have to run for weeks on some costs. Okay, so just to remind you, here's was the example spectrum showing the threshold for paraproduction is right around here. So in this particular model, it's the twice scattered photons that are producing, that are colliding and producing pairs. Okay. So here's the result. So this shows contours of constant paraproduction rate of density. And this is the axis, and this is the equatorial plane. And these are distances from the black hole and units of GM/c squared. And you can see that the paraproduction rate declines sharply away from the event horizon. So this line here is an approximate location of the wall of what's known as the funnel. This is the region that's nearly empty over here, and this is the region where the accretion flow and corona are active and where ordinary plasma probably dominates the wall. So, out here we don't really care about paraproduction because it doesn't make a significant contribution to the plasma density. So the accretion flow itself is at a far higher density, at least in the piece of perimeter space we're looking at. So again, almost all the paraproduction occurs right in here, hard by the event horizon. Oh, these, don't worry about the units for a moment. Those are arbitrary, actually. So in that last block. So, you do have to put a scale in for the unit to do this calculation. Pay no attention to the units in that block. Okay, so we've done all that, and we can't do this calculation every time we want to set a paraproduction. It's expensive. So we produced fitting formulae, and there's two different fitting formulas for the paraproduction rate density, which depend on the radius from the black hole and the latitude. And one is the paraproduction rate as a function of the accretion rate m dot in Eddington units, and the other is the accretion rate in units of the X-ray luminosity of the source. So that's X-ray luminosity divided by the solar luminosity. Okay, so this is a little disappointing for Monica. We worked on this, but we could sort of figure out what all these terms were going to be in advance. And in fact, we got the whole thing down to a dimensionless factor. of about 1 to 3 in front. So I won't go through that calculation, but you can understand why this should scale asymptotically as radius to the -6, because the photon density is going down as 1 over r squared. And then there's an angular factor in the cross-section that gives you another 2 factors of 1 over r. And you can work out all the same things. In addition, there's a dependence on the co-latitude. And this occurs because the intensity of the pair-producing photons is greatest near the equatorial plane. The plasma is moving around the black hole like this, and it tends to produce photons with wave vectors directed in the equatorial plane. So this we were able to work out in advance too, and this is sort of a pair production scale height, which is almost exactly equal to the density scale height, which is about 0.3 in radians. So there's a sharp fall off in radius. What wasn't obvious at the beginning was that the pair production rate should increase as 1 over r squared all the way into the event horizon, and it turns out that that's what happens. Yeah, I won't go into
So even
all
inside
these
the
answers.
answer.
Yeah, so there are photons that get captured by the wall, and that is a contribution to the production. Okay, so then the next step beyond this, which we're making now, is to put this model into a wind and look at what happens to the pairs after they're produced. But I just want to briefly describe the parameter space in which these things live and how the resulting plasma density in the funnel relates to the Goldreich-Julian charge density. So on this axis, we've got the accretion rate in Eddington units. And on this axis, the mass of the black hole in units of 10 to the 8 solar masses. So on this plot, Sagittarius star lives over here. It's like lower mass and about 10 to the -8. And M87 lives up here and 10 to the -6. And for all these calculations, I should say, we assume that the ion temperature is equal to the electron temperature. So to the right of this vertical red line, the plasma is cooling faster than it accretes onto the black hole. And in that state, our models aren't self-consistent. So our models really only lie with the latitude. To the right of these green lines, the density is above the Goldreich-Julian density. To the left, it's below. So over here, there are probably other processes that are determining the pair density in the funnel. And those may contribute over here as well. But the gamma-gamma pair production is enough here to raise the density of Goldreich-Julian. And then the Goldreich-Julian density inside the funnel is inhomogeneous. So along the axis, the condition is a little more stringent than along the boundary of the funnel where most of the pairs produce. Okay, so for a system like somewhere in between M87 and Sagittarius star, we would have a self-consistent model for the model. And for a stellar mass black hole down here, there's no system in which the models are both weakly radiated and produce enough pairs to raise the density of the
Could you expect that you might have some very large acceleration or you express all, and therefore see a lot of the power coming out?
It could be that happens even in systems that are here, because the model isn't going to be perfectly homogeneous. So there are waves helping to into the
Of course, from observations, you don't know what actually is needed about one EEV. From observations, you don't know the EEV radiation field in the vector. So it's the result of the production very, very sensitive to the actual flux in photons, which you calculate from the model. But from observations, you don't know. You keep accelerating particles a little bit, but of course, you can write this flux, which does not spoil the lower frequency particle spectrum. Then you can easily boost the connection rate.
Right. So it depends on the spectrum. Like we do have a and how much structure you think is in the spectrum you're wanting to use. But our models produce a spectrum of self-consistently, so we know what that is. Okay, so I'm going to leave curve correction for now and go on to the QPOs. And this is work that was done with my student Josh Goldman, who just finished up. Okay, so we can calculate a light curve at every wavelength for the source. And this shows the result of calculating the 3.8 micron light curve in a model of a Sagittarius star, and then taking the power spectrum. And again, this is appropriate for Sagittarius star, so there's a definite frequency here. This is frequency units of 1/minutes, and this vertical dotted line shows the orbital frequency at the innermost stable circular orbit for this particular model of Sagittarius star with a particular spin. And the black line, the heavy black line, shows the average power spectrum. So what we've done is taken a series of sensors and placed them around the equator of the black hole and measured light curves at each of these sensors. And then we've taken each of those light curves and split them up in a way that's designed to increase the signal to noise in this power spectrum. And then we've actually averaged, for the black line, all of the power spectra obtained by all the sensors that are spaced around the source. And you can see that this produces a bump near the ISCO frequency, and power, more or less a power law, low frequency. It's consistent with observations. It's about -2. And then a steeper drop off at a higher frequency. Okay, so one of the first things that we looked at when we found this was the spatial structure of the QPO. So we could go and decompose the power spectra into azimuthal Fourier components. So we could ask what's the n is equal to 1 power by, we're taking measurements at different sensors that are distributed around the source. It's not something the observers can do. And you see that most of this bump comes from m is equal to 1. And I should also add that this bump is highly statistically significant, and even the features in this bump are significant. Although if we split the light curve up, the features actually move around a little bit, so they're not fixed features on top of the bump. Okay. So most of this QPO is coming from n is equal to 1 fluctuations inside the source. The radiation has an n is equal to 1 structure, so the source is also having an n is equal to 1 structure. Okay. So having said this, I just want to back up for a moment and say something about our emission model. So we've assumed that the plasma is thermal. The electrons have a thermal distribution function. And this result may be sensitive to that. So, so here's our synchrotron, thermal synchrotron unicitic. This is the equation that we're using. And I'm putting this up because you can see there's an exponential factor in here. And the thing under the exponential is frequency divided by a characteristic synchrotron frequency. And the infrared emission is coming from the far side of this this exponential, x much greater than 1. And so small changes in the magnetic field strength or the temperature can drastically change the emissivity. And so there's a lever arm in there for fluctuations in the plasma to manifest themselves as fluctuations in the radiation. Okay, so having said that, we can go back and ask exactly where the infrared emission comes from. And because this is a Monte Carlo calculation, we can take each photon and track it back to the source and ask what the point of origin is in each of the cameras. And if we project those points of origin onto the surface of the accretion disk, onto the equatorial plane, then we get a footprint, or the infrared emission, that looks like this. It's like a snail on the surface of the disk. So the observer is off here to the right, and these infrared photons are generated here, which is inside the innermost stable circular orbit. And then they circulate around the black hole 1.5 times and come out over here. And they're generated very close to the hole because further out, the field strength is too weak and the temperature is too low to produce significant infrared emission.
What is the field strength?
It's like between 30 and 60 guys.
So charge frequency is way below. That's why you need high emission product. Not electron flux.
So this footprint acts as an effective filter for fluctuations in the disk. So if there's fluctuations that are limited as a neutral extent, they're not even going to be seen in the infrared. And this structure has a large n is equal to 1 Fourier component. And so it pulls the n is equal to 1 Fourier component out of the noise and puts it into the radiation field. Okay. So I'm on to my summary. So actually, before I go into the summary, I just want to say, the question I always get about this is, well then what's producing the QPO? And I'm a little embarrassed to say we don't have a clean answer for that question, but we think that there's a noisy system there with some modestly coherent oscillations in it, and then that filter picks those modestly coherent oscillations out of the noise. And the reason it's hard to get an answer is because they're deep in the noise. There's a lot of structure in the flow other than the m is equal to 1 structure that produces the QPO.
But the signal
What we do know
is very high, right? The observational. In your observations of your simulation.
Yes. The signal to noise for the QPO is high, but the signal to noise I'm talking about is the ratio of the amplitude of the structure that's producing the QPO to the turbulent noise inside of the accretion. So what we do know, in fact, is that it's primarily structures in the magnetic field that lead to the variation. So we can paste out, we can zero out the fluctuations in azimuth in every other quantity, and we still get the same magnetic structures. together a numerical laboratory for studying physical processes in black holes. On the convergence study, the magnetic field correlation is unresolved in our global simulation, and I think in every global simulation that's been done so far. But the spectra are relatively steady. So really, none of the MRI calculations are resolving well the outer scale of the turbulence, and there's no inertial range to speak of in any of the simulations, not in the global simulations or in the local simulations. We looked at pair production using our self-consistent estimate for the radiation field, and we've got scaling relations, so we can tell you how rapidly pairs are being produced at the sources, and if the models are accurate, where the pairs are being produced, so mostly near the event horizon. And then we found a QPO. It's dependent on our assumed distribution function for the electrons on our emission model. And we played a little bit with putting a non-thermal component in. We think that would certainly reduce the amplitude of this QPO. It's an m is equal to 1 structure. Lensing plays a key role, and we think it's basically the lensing that's acting as a filter and picking the QPO out of place.
We have time for questions.
So the cosmic ray has been included wrong with this AV plasma, but we confess when we become more relativistic. Would you ever hazard the gases that playing a role in the current flow? I mean, there's this inner, I guess there's inner light cylinder near the horizon, which doesn't work for stuff to get out. I don't have a sense of what the geometry of the accretion flow is in this case, right near the horizon.
Yeah, so it looks just like a disk that extends all the way in. And there's not a sharp drop off in the density close to the horizon. My guess is that there's a non-thermal component in the distribution function. Most of it's produced locally rather than by advection of cosmic rays from large distances.
So I think it was sort of controversial because doing code and which
No, go ahead.
well,
I have an opinion.
yeah.
Oh, we're being recorded.
Yeah.
No, I'm happy to. I've discussed this with the relevant parties. So, so between Julian and Ramesh concerning measurements of the spin and in stellar mass black hole systems, these are entirely from systems where the accretion rate is near the Eddington rate. And so there's presumably a relatively thin disk that looks like what Shane thinks it is have to look like. And there are, I think, two uncertainties here. One is the uncertainty related to the emission profile, surface brightness profile of the disk. And Julian and others have argued that there's an additional sort of hot component close to the isotope due to torques at the isotope. And Ramesh is argued that's not important. And then there's another uncertainty that comes from the fact that the inclination for all these systems is, for the inner disk, is assumed to be equal to the inclination of the binary system. And of the two, I think the uncertainty in the inclination is more serious. That there's no particular reason for the tilt of the inner disk or the spin of the black hole to be exactly aligned with the orbital of the system. And so if you tilt you increase the inclination of the disk a little bit, you make it appear smaller on the sky. And that tends to increase your estimate of the stage. the torque thing seems to be sort of 10%. It wasn't obvious that it would be a 10% effect, but the calculations seem to establish that. The numerical models that we think of. On the record.
Ask about, is there any possibility for the method of use to read or it's completely
I'm sorry, I'm very
sorry. You have the disk which has all the charges, particles, and you have this funnel with magnetic flux capture.
Yeah.
Is there any way, in these time dependent simulations, you have some connection? Is there any way for the method to read due to micro interaction or something? Is it completely
You're wondering if there's another way to feed ordinary plasma
If you
into
just
the
line the plasma integrated with the funnel rather than feeding plasma.
Of course, in principle, there could be. So I think one thing that could, well, first of all, if we start with a different field configuration, then the evolution does not include a strong magnetic field that protects the funnel from intruding plasma. And so that's a possibility. There's no sort of dipole to get into this. Another possibility is you get a reversal field. And that reverse field gets carried into the disk and reconnects. And there's an event where ordinary plasma gets fed into the funnel. And another possibility, which we could see in our simulations, is there's some kind of instability at the edge of the funnel. And we haven't seen that yet, but you sort of think that might be a very small scale process that we might not be resolving.
Not a very large, it's a small scale process.
Yeah.
So we just decide to resolve.
Yeah.